Hey, hi guys. So in this video we'll see how do we hide our text in an image. So this process is called as image steganography. In simple words, you take an image and you somehow hide your text in that image, and when you decrypt it you would get your text back. So in simpler terms, so we would have some text here, okay, and you also have an image which you want to pass. Let's say this was an image here, okay. This you pass through a script or a program and it gives you an output image, okay. So this image should be as identical to this input image as possible, and it will also contain the text which is hidden. So this would be our encryption part. And how do we decrypt it? If you give this image to our program again, it would give you back the text. So whatever you had written, you would get it back. So this would be our decryption part. Okay, so we write the code in Python. So we'll make sure we have two methods. One is encrypt and one more is decrypt, and we'll see through the whole process how it's done. If you just want to look through the code how it is working, you can skip to the end of the video. So basically we'll start with a little basic how do we do this, and of course we'll cover the code later. Okay, so before we begin, there are multiple ways in which image steganography is done. There are more than one ways. So a common way how they do image steganography is, so if this is our image, right, they put a small black border around this, okay. This would be a small black border. So when you see the image, it may look like a black border, but internally actually these pixels are written with some data, okay. So this is one of the common forms of image steganography, but the problem with this is you can visibly see a black border, so it may raise some suspicions, okay, that this is something different. So the image steganography we are trying to do is we try to keep the image as similar as possible. We try to have as many similarities and have very few differences. So we'll not be going through this border approach, which is easier to do. We'll be going to some other methods which are like more advanced than this, okay. So let's look through how are we going to achieve it. So the method we are going to use here is called as a least significant bit steganography. So basically this is called by various names, but basically the thing is we just use the least significant bit to store our data, okay. So let's see the initial part, okay. So this would be our input image, let's say. So we all know that any image would have three dimensions. So you would have height and width, and you have channels. So channels are basically color channels. So if you have a RGB image or a color image, it would be 3. If not, it would be 1 in case of black and white images. So here we'll assume that we are using color images. So internally, whenever you read a color image using Python libraries like OpenCV or Pillow library, you would basically get this format. So in this case, let's see, you would have your width, you would have your height, and you would have your channels. So in this case we have 3, that is RGB, okay. So each channel here consists of some pixels, okay. In this way, so it keeps on going. So basically, if you have, I'll take an example of, if you have an image having 10 pixels height, 10 pixels width, and 3 channels, okay. So in total you would have 10 into 10 pixels, which is 100. So each layer in this way would have height into width number of pixels, okay. And how many channels you have? 3. So in this case you would have 300 pixels, yeah. So this is the basic calculation. You have height, you have width, and you have pixels. And in case of an RGB image, so if you take for example 1 pixel, it can have values from 0 to 255, okay. So based on the combinations of these colors, we get the whole color gamut. So all you need to know is each image is of the form height, weight and channel, and each pixel has values from 0 to 255. So this would be our basic thing. So let's see how we'll go through. So the first process we'll do is, so we do not want these three layers. So what we'll do is we'll convert this whole thing into a one-dimensional array. Okay, we'll do in this way. We'll convert the whole thing to a 1D array. So there are functions in NumPy called flatten or similar functions in which you do this. So how many? So 0th pixel, 1, 2, 3, 4 pixels. So in total you would have height into width into 3 pixels, because we're assuming color image here. So we saw we have 10 pixels here, right? So in this case it would be 0 to 300. Okay. Basically what we are doing is we are cutting single pixel and we are joining them. So instead of having 3 different layers, we are actually concatenating all these pixels to a single array, so that it will be easier for us to manipulate. Okay. So let's see how our encryption would be done. So I'll take an example of, let's say we have a text called as hello. This is where the LSB Steganography comes into picture. Okay, this is our input text. So I'll assume we have one character for each. Okay, we split our sentence into characters, HELLO. Okay, now what we do is, okay, we get the binary representation of each character. Okay, so if you get the binary representation of H, you would get some value. I'm not here referring to the exact value, but if we have functions called as ORD in Python, which can give you the exact ASCII value of this character. Okay, and that ASCII value is generally between 0 to 128 for characters. If you have special symbols, it can go up to 256. So we'll assume that we have only some special characters like exclamation, dollar and text, but we can also extend this to higher more complex symbols like smileys, emoticons and everything, but we'll assume that we are dealing with 128 bits here. So what you do is, when you pass this character to certain functions in whatever functions, so it will give you a binary representation. So let's say you get, okay, so let's say this is the binary representation of H, let's assume. Similarly you'll get the binary representation of E also. Okay, in this way. Okay, so with this you can note that this would be a 7-bit number or a 7 binary digit. So in this way you'll do the same for all the characters, so whatever are there, so L and everything. Okay, similarly you will do to the end. So if there is a space, even space has an ASCII representation, and even that would be encoded into a 7-bit binary number in this form. Okay, so what we'll do is we'll pick up a pixel from here, okay, from an image. Let's say a pixel is picked up in this form. Okay, we saw that we had values from 0 to 255 in each pixel. Let's say this had a value of 10. So internally when we refer to 0 to 255, these are also binary numbers. So you would already have a 7-bit integer. So let's say we have 255 already here, or 256 already here. So in case of 255 you'll have 5, 6, 7. So when all are ones, this value would be 255. If you have 0, you would have somewhat like this. Okay, so let's assume you have a value of 255 in this block, so you would have something like this. Okay, so what I'll do is, okay, so this is a pixel, and remember this will have some values filled previously. based on your pixel density and pixel color. So this is basically an image. So one pixel will already have a binary number field like this. So what we'll do is we will take h first, okay, and this bit will put it to the least significant bit of pixel 0. Got it? So here it was 1, we'll replace this and we'll make it a 0. Okay, so similarly let's assume you take the second bit here from second pixel, okay, second pixel from the image. Similarly you would have something filled here also. This is the second pixel, so from here you would put it to the least significant bit of the second pixel. So we have 1 here, so we'll make 1 here. Okay, so we'll make these sort of changes. So basically what we are doing is we are getting our pixels. By pixels I mean this array. So this first bit of our text character will be putting it into the least significant bit of the first pixel. Second will go to the least significant bit of the second pixel. The third will go to the third pixel, in this way. So if you observe, so each character will have 7 bits, okay, 7 bits, and each bit will go to the least significant bit of each pixel. Okay, that means you need 7 pixels to encode one character. Okay, so if you see 5, 6, 7, this will go here, the least significant bit. This would go to the least significant bit of 4, this would go to the least significant bit of 5, and this would go to the least significant bit of 6. So in total these 6 indexes, or 7 bits if you count, okay, so 0, 1, 2, 3, 4, 5, 6, 7. So these 7 bits or 7 pixels of the image will represent h, Similarly the next 7, let's assume this as next 7 till 13, this would represent e. Okay, so we'll go to the same thing, this will assume L, similar to this path. So this is the whole thing. So now we would have one question obviously here, is why least significant bit, and will our image change in this case? So let's see why we are using least significant bit and not most significant bit. So as we saw previously, right, so whatever value we have in our pixels, okay, let me write it down. So we already discussed that it would be 7 here, 7 bit. So 1 0 0 0 0 0. Let's assume this is the pixel value, this is the pixel 0. Okay, if you observed, we are only replacing the least significant bit here, whether it is either 0 or 1 based on our character. So in totality we are just changing LSB, this bit, and not this whole bit. So this would remain same, this whole thing would remain same, only this would vary. So if we look at it in total, we are just changing one part of the information, and this part of the image will be preserved, this whole thing. Yeah, coming to the question, why LSB? So as the name itself mentions, the least significant bit is the rightmost bit, and it has the least impact on the total value. So if you go to the binary representation, okay, you know that this bit is 0, 2, 4, 8, 16, 32, and so on. Yeah, so let's assume 16. Okay, this was 16, 0, 0, 0. 8, yeah, this is 16. Okay, so let's assume I change the MSB to 0. What would be the value of this now? 0. Okay, ideally we had 16, the value of this is 16 here, 16. Let's assume I change the MSB to 0. Okay, I'll get completely 0. Let's assume I change the LSB. Okay, let me make the LSB here to 1 in this case, so it would be somewhat like this, right? So if you see, this would be 17. Okay, when you compare this value to the original value, here 17, 16, there is a 1 difference, and here there is a 16 difference. Okay, so this difference is huge. So this makes a impact, because if you totally replace 16 by 0, you are losing out on 16 bits of information ideally, but here you are just losing out on 1 bit of information. So let's assume you had a pixel which was of value 255. Okay, so 255 is the highest intensity. Okay, in now let's assume your first bit of your character was H. Okay, and that is 0. Okay, if you make the MSB as 0, this whole thing would come down to 0, which is extremely bad. You would not want this. So the difference is something as your black pixel would become white. So assume your image was having a white background. If you replace MSB, in some cases maybe the white background becomes black, and that would totally spoil your image. But let's assume you just change the LSB. If you change the LSB, there can only be +1 or -1 difference. So if there is 255, it can either be 254 or 256. Okay, when you change the LSB. So if the LSB was 1 and you made it 0, okay, it will become 256. Oh sorry, 254, it would reduce. If it was 0 and you made it as 1, it would increase. So 255 would become 256. So there is only one change. So 255 going to either 254 or 256 is just 1 pixel intensity difference, but going from 255 to 0 will make a drastic difference. So basically 255 and 0 are the end spectrums of the color. So if 255 is white, 0 would be black, totally opposite. So if we just replace MSBs, it would be really hard to maintain the actual image. So we'll replace the least significant bit. Yeah, so this was all the theoretical part. This was the logic we use. So without wasting much more time, we'll just go to the code part now, how we are implementing it. So we have made a class called as image steg. You can do anything. So I'll just go through a brief pattern which we are following. Later, if you want, you can go through the code in depth. So we have a function called as encrypt text in image. It takes an image, the image path, which image you want to encrypt. It takes an image, and it also takes target path, that is where you want it to be stored. Okay, so this is the whole process we are doing. So we read an image, we flatten the image, we encrypt the images using least significant bits, and we reshape. So the reshape part is simple. So as we discussed, right, so here we have a 3-dimensional image. I'll just clear everything out. Yeah, so we have an image which is 3-dimensional initially. I mean height and width and band. We saw that we would flatten this out completely. Okay, this is what we would do, and 7 bits would make one character, C, H, whatever. So we saw that we'll be using LSB to minimize the change here, and we would only change the least significant bit. So once this is done, if you want to save back the image, you want to get it in this format. So what we'll do is we'll just reshape this whole array into 3-dimensional array again. We'll do this. So this is just to so that the input and output are more similar. You take an image in this way, you flatten it out, you do all the encryption, But before saving, because the computer expects you to save it in this format, you save it in RGB format back again. So that's the whole concept of reshape and repack once again, and you return an image. So if you see here, I'll not go into the library details. I'm using Pillow library here, Python Pillow. You can see Pillow. So in this line, I'm reading the image, okay, as an numpy array, and here I'm just using flatten. I'm using the flatten image here, okay, and yeah, and whatever image you pass, I'll append the tag called as end. Okay, so I'll explain you why this part comes the end part here. So what we'll do is our message, whatever we give the message here, we will convert the message into an array of binary values. So I have written a function called as fill MSB. So what this basically does is it converts. So if you have alphabet A, if you have an alphabet A, okay, it gets the ASCII value of this, which would be something in this format. It gets the ASCII value, it converts this whole thing into an array of this format. So basically you'll be having somewhat like this. So this would all be binary numbers. So you have 7 bits, 7 bits and 7 bits. So that's what we do in this part. Here you convert your whole message into binary representation and an array. Okay, yeah, and this whole part deals with our MSB logic. That is, if your bit is 0, okay, you set the LSB to 0. If the bit is 1, you set the LSB to 1. So you can go through the whole thing here. I use some for loops and if statements here. This is pretty simple to do in Python. So I have done it manually, but there are some libraries which can do the same for you. So there are some libraries in which you can specify the MSB bit to replace, and that can be done. But I am using a custom approach here. This is the part we had discussed. So for each bit or each character, you have 7 bits. For 7 bits, you fill 7 pixels, and at the last, you store everything into an image array. So if you see, I'm modifying the image array everywhere. So basically I'm taking the pixel of image array and I'm setting it to either 0 or 1, the last bit. Okay, and the message array is your message which needs to be encrypted. So whatever you pass, so let's say I pass hello as a message, I iterate through each character and I use this fill MSB to get the binary representation of each character, and then I pick 7 bits and do it. When everything is done, I save the whole path, save the whole image. So before saving, as we had discussed before, I just reshape the image or the image array to the actual image shape. So if the image shape was 100 by 100 by 3, so at the last, before saving, I just reshape it back to the original dimensions, img array img dot shape, and I do just the save part. This is Python basic function, so I just save. So whatever path you have given in this save path object, we'll just save it there. So just as an easier to notice, we'll append it with an encrypted.png tag. So if our image name was image.png, we'll save this as image underscore encrypt.png. So just for an example here, I take, okay, so I have imported the image Steg class here. Okay, create an object and I call this function encrypt text in image. So this takes 3 arguments: image path, message and target path. So let me show you the image here. So I'll be using an image of a leaf, very simple, a white background, a green leaf. I'll use this. So I'll pass this test.jpg, okay, test.jpg here, and I'll pass my image message which I want to hide. So I'll say hello, this is my hidden message, and where do I want to save it? Save the encrypted image. I'll show it in the static part. Okay, in static. Let me just run this and check if everything is working fine. I'll just run my code. Yeah, let's see if it was created. Yeah, so if you see, this is the encrypted image. This image in it has our text message hidden. So as we have used LSB Steganography, I'll show you the difference. Okay, So the image on the left is the original image, and on the right is the encrypted image. If you see, there are no visible differences in this. We had discussed a trivial approach in which we put a black border, so we do not use that case here. So if you see, these two images are practically indistinguishable to the human eye at least. So if you see, there are no obvious changes or obvious color changes everywhere. Okay, so that is because we are using least significant with steganography, and the pixel values would differ only by 1 point or 1 pixel color, and that is really hard to distinguish by the human eye. Obviously, if you pass this through a program and compare each values, you would get certain difference, but in normal viewing it's practically impossible to determine which image is modified or has some text in it. Okay, so let's go to the decryption part now. So decryption part is pretty simple. So we read the image, okay, in this form. Same, we convert the whole image to a array, flatten array. Okay, and previously we know that from our experience here, we know that 7 pixels. Okay, so let me write it down here. So if you take 7 pixels, okay, and you get the least significant bit of each of these pixels, let's assume I get it somewhat like this, 7. Okay, this is nothing but your single character. Okay, you can do this. So there are functions in Python. I think binary function works fine. So if you pass it through a method like binary, this would give the binary representation of 250 or something, just an example, and you can then convert this back into ASCII value. Let's see. So basically you read an image, the decryption part, you read an image, okay, you make group of 7 pixels in this form, 7 pixels, 7 pixels, okay, and if you take the least significant bit of each pixel in this pixel, you would get an ASCII value of A or B in this way. So basically 7 pixels would give you 1 character, and you go on appending these characters. That's what we are doing here basically. Okay, so if you see the for loop here, I'm putting a range from 7 to the end of the array, and I have a step size of 7. So in each iteration I'm picking 7 pixels. So I'm decrypting 7 pixels at once. So when you decrypt 7 pixels, you would get 1 character, and I have a global variable called decrypt message where I keep on extending. Okay, and if you observe, before we had put a end tag. So why is this? So just for an example, okay, when you're encrypting, let's say your message was hello, okay, and you encrypt this in an image, okay, and you get an encrypted image. So when you decrypt this, back, so let's say our image was of size 100, 100 and 3, okay, so you have 300 pixels, and you have hello was our message, so 5 characters, 1 2 3 4 5, and each character needs 7 bits, so totally 35 pixels were used out of 300. So that means that 215, so 215 pixels were untouched, sorry, 265 pixels, and only 35 pixels were encrypted. Okay, so when you decrypt, you do not know exactly how many pixels to look for when you're decrypting. So when I decrypt it, right, I'll get an array, I'll flatten the image, I'll get an array from 0 to 300 pixels. Okay, I'll group it into 7 pixels each. From each I'll get 1 character. Let's say I'll get here H. From this I'll get L, 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 O. Similarly, because we don't know how many pixels, you will always keep on getting some values like this, so on. So we don't know where to stop. So there are two approaches for this. One is the delimiter approach, and second is the length approach. So in length approach, what you would basically do is you would actually store the length of your text, okay, in the first pixel here. So this first pixel would only store the length. So let's say it would store as the length as 35 pixels, and your actual message would start storing from the 8th pixel onwards. So basically in this case, what you would do is you would read an image, okay, you would read the first 7 pixels, which will give you the length, okay, and then you decrypt only the length amount of pixels. That is one way which it can be done, but we are using the second way, that is the delimiter approach. So in delimiter approach, what we do is, if your message was hello, you put some delimiter here. So in my case, the delimiter is end, okay. So what happens in the decryption part, it is pretty simple to do. We just do this, we encrypt this whole thing as our message, and when we are decrypting, the first 7 pixels would give you H, okay, the next 7 pixels would give you E, similarly L, and then O, and then subsequent pixels would give you /END, okay. And so whenever you get this END in the decryption part, you stop the decryption here and you just ignore whatever else was done there. So you just give this as output. So in this case, you are just processing these many pixels. Wherever you find end, you stop and you just return. So that's the whole concept of delimiter. So here if you see, we'll check if the last character or last 7 characters are END. That's because the length of this whole string is 7. So if you see 1 2 3 4 5 6 7, so you can use any custom delimiter here. I have used end in this way. So it's simple. So whenever you see that you have encountered this end, you just break and return. So let's see decrypting it once. Okay, so I'll create a class. So the decrypt method takes in 2 arguments. One is the image path, okay, that is from where do you want to get the image, okay. So I give image, and where was our image? It was in static and test encrypted. I'll give this, and what it returns is the string or the message. So if I just run this code, we are expecting to get a message which we had previously given. So if I return, see, this was the message. So this was extracted from this particular image which was there in test encrypted. Yes, so that's the whole process of image steganography. So this is using Python, very simple code. So if you want to add more and more sort of security into this, you can also add encryption part, which can be done, but for this here we'll not be going through that part. So encryption also is very commonly used. So just give you a brief overview of that. So here what we are doing is, we have the text and we have the image. We give both of this, okay, to our program, and in return we get a encrypted image, and you send this through Google or anywhere to any person. Once he decrypts this image back, okay, this is the encrypt part and this is the decrypt part. So when he decrypts, he would get the text back, okay. What you can do here is, you can add one more level of security, is that when the user gives in the text here, okay, before combining it with the image here, you can encrypt this text, okay. you can encrypt this text using AES encryption or SH256, any popular methods. So while encrypting, you would have a password which only you would set. Okay, so you would do this. So what the code will do is, it will take the text, it would encrypt it using a password you give, and then it would combine, the combination steps would be the same. It would combine it with the image and give you the encrypted image part here, and then you would send it to any user who wants to use it. So when he gets the image, okay, and he extracts it, he would not get the exact text but instead he would get the encrypted message. Okay, this one, whatever you got here, this is what he would receive. In order to decrypt this, he would also need the password. Once he gets both this, only in this case he would able to get the text. Okay, so for whoever wants to access, he would need this image, plus he would also need the password. So this provides a 2-level of security. So let's say you did the encryption, you took the text, you encrypted using some password, and you put it into an image and sent it. If somehow the attacker is able to get your image decrypted, even if you manage to do it using if he reverses your LSB steganography logic and he encrypts it, he would only have the encrypted text. In order to fetch the exact text, he would still need this password, and you would have to crack this password using brute force or some other methods. So this provides you a 2-level security. So implementing this would be really easy. So you have inbuilt libraries in Python which can do it. There are libraries which provide AES encryption. There is a library called Fernet in Python which also allows you to do a basic encryption part. So you can just extend the same code to also do the encryption part. So in that case, when you're encrypting, along with the message, you would also need a password which needs to be sent. And this would act as your encryption password. And whenever you decrypt, you would also need a decrypt password here. Yeah, you would also need decrypt password. So that would be the whole process. Yeah, so I hope this was of some help. You can go to the code. If you have any optimizations for this, you can surely try them out. Yeah, I hope that was helpful. Yeah, thank you.